Welcome to today's Explainer, everyone. I am absolutely thrilled to have you all here. As graduate students, and really as future researchers, you are standing right at the edge of a massive shift in how we understand human behavior. Today, we're focusing on mastering large-scale text analysis. So, let's dive right into this explainer and unpack the exact methodology that allows us to make sense of the millions of digital conversations happening around the world every single day. I want to kick things off by posing a very real and honestly a pretty daunting Socratic question. How do you accurately analyze 200,000 tweets without actually reading them all? Really think about that for a second. We are currently facing a modern fire hose of unstructured social data. I'm talking text files, emails, open-ended survey answers, massive streams of social media. It's raw, it's messy, and the sheer volume makes manual reading a complete impossibility. So if you want to know what the public truly thinks, you absolutely need a methodology that scales. Here is our syllabus for today's intellectual journey. 1. The Big Data Challenge. 2. The Human-Machine Loop. 3. Training Adaptive Algorithms. 4. Applied Research at Scale. And 5. The Future of Social Data. Let's get right into it. Starting off with Section 1, the Big Data Challenge. You see, the absolute core problem with unstructured text is figuring out how to separate the noise from the actual signal. Take an actual study by the Health Media Collaboratory in Chicago, for example. They were researching social responses to public health anti-smoking campaigns. To do this, they opened up the Twitter fire hose to search for the word smoking. And what did they get? Absolute, unfiltered noise. A basic keyword search pulls in millions of totally irrelevant tweets about, smoking hot girls or smoking barbecue. But what they actually needed was the targeted signal, which was people talking about smoking cigarettes or quitting smoking. Without a reliable way to sift that signal from the noise, your research is instantly paralyzed by irrelevant data. Moving right along to Section 2, the Human-Machine Loop. This brings us to what I like to call the conceptual magic sword needed to defeat this big data monster. It's a crucially important concept known as the human-in-the-loop methodology. We really have to establish this as our academic lexicon today. Too often, people think algorithms are just these magic black boxes that magically do the work for us. Well, they aren't. Algorithms require intense, incredibly precise human observation to achieve pinpoint accuracy. This methodology uses human intellect and manual coding as the indispensable foundation to train automated machine classifiers. The software platforms we use, like DiscoverText, are engineered specifically to mix human and computer training in this elegant, powerful loop. Okay, let's actually walk exactly through this algorithmic workflow step by step. Step 1, you filter the raw data. You take that massive fire hose and capture a sample based on metadata or keywords. Step 2 is human annotation. This is where researchers actually read this small subset and code it. They give it a label. Step 3, we adjudicate reliability, which basically ensures that the humans actually agree on what those codes mean. And finally, Step 4, machine learning classification. Those human observations feed directly into an adaptive active learning engine, which then creates a unique point-in-time measurement for the rest of the unread data. Essentially, the human teaches the machine, and then the machine processes the scale. Which brings us to Section 3, training adaptive algorithms. So actually building a binary classifier requires a very strict methodological exercise. In a real-world example from Dr. Stu Schulman, the research goal was to predict if a chunk of text fell into a specific category or not. In this case, they were looking at whether political Twitter bios were promoting or not promoting a specific political figure like Donald Trump. Now, as data scientists, our job is to remain strictly impartial here. We are not judging the politics. We are simply categorizing unstructured text. By looking at a user's description, totally disconnected from personally identifiable information, we can impartially label the text to create a very clean binary training set for our machine classifier. 400,000. Just let that number sink in for a second. That is the massive volume of manually coded items that went into forging just one single robust predictive model for political bios in DiscoverText. I really want that to create a sense of awe for you. You don't just click a button to get machine learning. It requires a significant corpus of human annotations. You build a model by feeding it tens of thousands, sometimes hundreds of thousands, of labeled items, carefully balanced, so the machine learns exactly what the target text looks like. So you might be wondering, how do you efficiently find the right data to code so you aren't just reading randomly? Well, you combine advanced filters. A researcher can set what's called a likelihood score, which is basically asking the machine for items it is 95% confident belong in a certain category. Then you filter for items with a coding status of uncoded, meaning humans haven't laid eyes on them yet. Finally, you add specific keywords. By combining these, you pull a highly targeted sample of, say, 800 items out of 160,000. You rapidly code those 800 items, feed them right back into the engine, and the machine learning model continuously refines its own accuracy. But wait, if human input is the absolute foundation here, what happens if the humans are, well, wrong? That brings us to adjudication. You must measure how well humans actually agree with each other, which is known as intercoder reliability, before you can ever trust a machine to classify the rest of your data. You pre-test your coding schemes. You have multiple researchers from entirely different cultural backgrounds collaborate and code the very same data independently. Then the system compares their work. If the coders disagree, the codebook isn't clear enough. By adjudicating these disagreements, we exclude inaccurate choices from the machine training data. At the end of the day, better human coding equals better machine learning. All right, on to Section 4, Applied Research at Scale. The sheer scale of these real-world applications is literally staggering. For public health, researchers didn't just want a small sample of reactions to a tobacco prevention campaign. No, they used API tools to capture the entire Twitter fire hose, evaluating intermediate health behaviors before people actually went ahead and quit smoking. Meanwhile, over at the USC Scenario Lab, they looked at climate change by analyzing hundreds of millions of global messages across multiple languages. They were sorting through the noise to understand exactly how people globally make sense of their changing environment. And this massive scale is exactly what proves the irreplaceable value of keeping a human in the loop. In traditional communication research, there's always a real danger of researchers imposing their own assumptions onto the data. But by carefully, manually reading the data, the USC Scenario Lab discovered some wildly unexpected local narratives. They found that people weren't always talking about saving polar bears. Actually, Californians were highly emotional about having to tear up their front lawns because of water reductions. In Europe, people were terrified that climate change would ruin their favorite French cheese or wine. Furthermore, researchers had to manually decode emoticons, basically figuring out if a smiley face was representing genuine sadness about the environment or just deep irony. A machine alone misses that nuance entirely. A human catches it, codes it, and then teaches the machine. I want to share a direct testimonial from an academic peer review here. When you are doing these huge, large-scale dissertation projects, public comments and social media repositories are absolutely awash in duplicates and near duplicates. Think of a massively retweeted message or an email template with just a few minor edits. Algorithmic clustering actually groups these documents based on similarity, highlighting the minor additions or deletions. This automated deduplication is a total game changer. It saves researchers from endless, tedious, repetitive tasks with Sharpie pens and giant spreadsheets, freeing up your intellect for actual meaningful analysis. And finally, Section 5, the future of social data. Because look, with global, multilingual data comes massive power, but also immense responsibility. First and foremost, you must rigorously abide by your institutional review board guidelines. But honestly, IRB just isn't enough. You have to establish a strict do-no-harm framework. This is especially crucial when researching sensitive topics like political unrest or health crises, ensuring you never inadvertently put an individual in the line of fire. You have to navigate incredibly complex, ever-changing international terms of service, which very often conflict with local laws. And finally, methodologically speaking, you must learn to distinguish between a massive organization acting as a public broadcaster and a private individual just sharing a fleeting thought online. I want to leave you all with a final provocative thought today. You now know the methodology. You understand how human intellect pairs with automated machine power to tame the big data monster. But as future researchers, as the people who will actually be out there building these models, how will you responsibly wield the power of adaptive algorithms to predict human behavior from social data? The tools absolutely exist right now to uncover the hidden narratives of the world. The responsibility of what to do with them, however, rests entirely with you. Thank you so much for joining me in this explainer today. Keep questioning the data, and I'll catch you in the next one.